Tonight's event is called Invisible Infrared, connecting the James Webb Space Telescope and climate change with Dr. Karl and Professor Peter Tuthill. My name's Fenella Kernebone. I'm the Head of Programming for Sydney Ideas. Again, it's great to have your company. Before we continue, I would like to acknowledge the traditional custodians where we are gathering today, and also where you might be watching our live event online as well. I also want to recognise their continuing connection to land, to water and to culture. We're here at the Charles Perkins Centre in the auditorium. It's a great privilege to be here on Gadigal land of the Eora Nation, and I would like to pay my respects to elders past and present. Further, I would like to acknowledge the traditional custodians of country where you live, where you work and where you might share your ideas, wherever you happen to be with us today. And I pay my respects to their elders as well, past and present. And I also extend that respect to any members of the First Nations community who might be here with us today. Again, a welcome to our speakers tonight. We're so excited to have them here. They're going to take us on a guided tour of the latest photos of the James Webb Space Telescope, or the Just Wonderful Space Telescope, and so many more exciting things to come. I'm really thrilled to have with us in the room Professor Peter Tuthill. He is an expert in astrophysical imaging. He's also the only Australian who has an experiment on the JWST. So we're very thrilled to have him in the room. Also joining him is none other than Dr. Karl from Triple J to his University of Sydney podcast, Shirtloads of Science, and everything else in between. Would you please welcome our speakers, Professor Peter Tuthill and Karl.
Thanks very much, Fenella, and it's awesome to see a live audience here today. And so let's just kick things off. We're here to talk about the most amazing big thing happening in astronomy today, and that's the James Webb Space Telescope.
JW stands for Just Wonderful, and this has got a huge mirror, 6.5 metres across, and underneath you can see, I'm just going to try this little thing here, maybe working, not yet, it'll come good. You can see down at the bottom there's this amazing shield. We'll talk more about that later. And what we've also got for you is a quandary. How do we go from a telescope to climate change? Peter, what do we do?
Yeah, so Karl, that's where we're going today. This talk you'll all be experts in the infrared by the end of today. So the first order of business, Karl, I think we better give the audience some knowledge they can use, something they can take home with them and impress their friends.
So what we've got for you is a foolproof way where you can look at a photograph and say with great 100% confidence that came from this telescope or that telescope. Useful geek knowledge. How do you do it? Well, you start off by getting a picture, say, of a galactic cluster. SMACS, bunch of letters, numbers, whatever, and you get one photo on one side, and then you get another photo on the other side. Which one was taken by which? The first thing is ignore the brightness, the contrast, all that, because they're all different photos. Instead, find a star. Look carefully. See that it has points. If it has 4 points, it's a Hubble, and if it's got twice as many points, it's at least twice as good. It's a JWST. You'll see there's 6 plus 2 off at the side.
So those spikes are in fact an artifact. They're due to the way the mirrors are shaped. And we're going to go on a bit of a deep dive later in this talk into the technology of this wonderful telescope.
And part of the technology is the fact that it weighs 6 tonnes, and Peter has got some hardware. Knowing the sort of guy he is, I reckon it's pretty big. The thing uses about 2 kilowatts, enough to run your dishwasher at full rate or your washing machine at home. And it is huge, 20 metres by 14 metres. It is an absolutely enormous thing. And here you can see the primary mirror on the Hubble. That was the older one, put up in 1990, and it's sort of about this much, 2.5 metres. On the JWST, you've got 18 mirrors, each of them gold covered. Why are they gold covered?
Well, gold, it turns out, is the new silver if you want your telescope to work in the infrared. Gold is really beautifully shiny all through the infrared, and we'll come to that again later on.
And if you have a look at the New South Wales trains, you'll see they've got a thin layer of gold. That's very good at reflecting. There are 18 individual hexagons mounted to some incredible accuracy, and that's your big fat telescope here. And just to give you an idea of the scale of it, you've got over here a mock-up of it, and notice that there's no barrel around the telescope, right? And they've made a mistake. Peter is not in there. He should be here. We'll Photoshop him in there a little bit later.
So if we scale that mirror, that big gold mirror, up to the size of Australia, The segments would be about half the size of New South Wales, and the engineers, to get the telescope to work, had to align them to about 4 centimetres precision over that scale. That gives you an idea of the stunning engineering required here. And even more amazing is you might get a system to work like that, and then you've got to pack the whole thing away and stick it in the front of a rocket.
A rocket that is only 5.4 metres across. So how do you stuff something 20 metres across in it? You fold it up there like a bit of clever origami, and you can see that that's the illustration. And like all illustrations, it's smooth and beautiful and lovely. In real life, it's a bit rippledy and messy, but it actually does work. That was it just before launch.
And I want to convey the white-knuckle moment that astronomers like me have been having, or moments, while this thing's been out there deploying itself and flying, because this is $10 billion you're looking at. Astronomers don't get to play with $10 billion, not even every other decade. And if there was one of 344 failures along a critical path of deployment, the thing might not have worked at all. So we're very, very lucky that it did so. But this big gamble that we just had has
paid off big. Big gamble, big outcome. And this photo actually turned out to be, I know this is a weird thing to say, annoying for you astronomers. It was kind of annoying. It gave you more than you wanted.
Yeah, before we go further, just let me give my first impression of an image like this, because I was actually in touch with a lot of the guys who were responsible for deploying this, for aligning it. And one of the funny problems we had is that the images like this are so swimming with galaxies, everything's just bursting with science, that it was hard to find a nice little corner of the chip to calibrate anything. You couldn't find a nice clean piece of sky just to look at, just to get a simple image of anything.
It had too many galaxies, which is not sort of the problem that astronomers normally worry about. So let's zoom in a little bit more, and then we'll find something interesting. We're looking through great depths of time and distance and time.
Yes, so we see things here in the foreground. They'll often have those points we talked about. Things in the middle distance, these are galaxies, and then things way off in the background. So the first thing you might, if you want to again impress your friends, you've heard of a thing called the redshift, the astronomical redshift. Your first guess, if you want to impress someone, is say, the redder it is in a frame like this, and this is just showing us astrophysics, cosmological astrophysics in spades. If it's red, it's probably further away.
Second bit of handy geek knowledge. Now, so when you look more, the thing that struck me was, see where the arrows are? They look like they're pointing to broken bits of a curved reddish circle, and there's some close in, and then there's some further out, like a fragmented circle just sort of strung out. It seems like they're almost bending around something. Peter, what do you reckon?
Yeah, so Karl, this image shows a thing known in astronomy called a gravitational lens. And when you have an intermediate distance object that's very, very massive, the gravity itself warps the space, or equivalently warps the light. So the light from the distant object goes in a curved path around it. And we're kind of seeing this kind of lens made out of gravity in the foreground, warping this image. And in fact, these lenses can be so strong that you can see multiply imaged systems. And that set of 3 galaxies there's 2 with a squashed banana-looking red one in between. That's the same galaxy off there in the upper right and then the lower left. It's the same distant object with 2 sightlines to it through this very curvy, very trippy warped space that we're seeing with Webb.
So you photograph something and you get an image here and an image there, and it's not because you've had too much to drink, it's actually real. So there's one thing that we have not quite mentioned, and it's the fact that we've got a heat shield. And why do we need this big fat heat shield? And if you have a look at this video here, you can see that the 5 layers are being pulled out, but if you look at the bottom, the amount of power coming from the sun is 200 kilowatts. That's a lot. And out the top is 10 times less, 23 milliwatts. So it's sort of sitting there. This telescope is sitting in the shade. It cannot be illuminated by the sun or the moon or even the earth. It has to be forever in total darkness. Which is that why it doesn't need a barrel around it?
It's a factor of 10 million times attenuation of the sunlight. So you've got, on the bottom, you've got 200 kilowatts from the sun, and less than a laser pointer, or an average laser pointer, is coming and warming up the telescope itself. So it's an incredible engineering system that is performing this job.
So we're talking infrared. We're keeping the heat of the sun away from it, not even the heat of the moon. can land on it. And here you can see we've got our scale. And the visible, which is what our eyeballs have evolved for, yes, the Earth is not flat and evolution is real. So our eyeballs pick up that range there. Then we put up the Hubble Space Telescope. And the Hubble got visible, a bit of ultraviolet, and it kissed its way a little bit into the infrared, but we wanted more. And then up came the Just Wonderful, and it's deep, deep, deep into the infrared, going up to 27 microns. I'm not sure what your hair is about 60 microns thick. So here are some of the gorgeous images. And you saw that there were two bands that we were looking at. And over on the left, you've got near cam, that's near infrared. And over here, you've got MIRI, and that stands for medium. And this is, what exactly we look at? This is what our sun will do at the end of its life. It'll throw off something like 20 or 30% of its mass away. And if you go looking a little bit deeper, Peter, what do you see?
So this is a thing called a planetary nebula. And our own sun will have a performance like this at the end of its life. It'll throw off its envelope in a spectacular sort of final act. And it's tempting to see that bright blue star as being the guy that's doing all the work here. That looks like in the middle of it. But in fact, if we take the magic of the infrared, and this is really where the Webb comes into its own, you can see that that star, if you actually split it with the Webb, you can see there's a faint red one right beside it. That's the culprit in this crime scene. The blue one is just a bystander in the whole game. So Webb is revealing us this invisible world.
And it's doing it through the magic of infrared. Here we get another set of galaxies. This is Stefan's quintet. Once again, NearCam and MIRI. Take us through it, Peter.
Yeah, so this is a much nearer set of galaxies than the ones we showed at the very beginning. And you can just see immediately, without even being told by an astronomer, the power of the infrared. The image on the right is with the MIRI camera. That's further into the infrared. It looks like an X-ray, doesn't it? Looks like you've taken an X-ray of those galaxies. It's exactly what you've done. The infrared burrows right down and sees into the core of things, just like an X-ray. It goes right through all this obscuring dust. So what's actually happening here in Stefan's quintet is actually a common theme in astronomy, and that is fireworks. Often we find in astronomy, when we look out there, it's a pretty violent place, and these are galaxies that are all dancing around each other and colliding.
So what happens when you've got dancing? You know, your parents told you, learn as kids, after dancing, the Presbyterians know this, you get babies. And the babies are born in nurseries, and this is a stellar nursery. There's about 7,000 of them in our galaxy, the Milky Way, and this is where stars and planets are born, and the stuff they're made of is what maybe other stars have thrown away, and also stuff left over from the Big Bang. You know more about that sort of stuff than I do.
That's right. So with imagery as good as this, you almost don't need astronomers, because the picture just tells the story. You can see this massive cloud of dust and gas at the bottom there, and inside that cloud, stars are furiously being born, assembling planets, assembling their mass. But actually, you can also see a bit of a parable here. It's a race against time, because up on the top, you can see these ferocious blue stars have already turned on. Once they turn on, they start burning that cloud away with ultraviolet, with fierce winds. The stars down there better get their act going quickly, otherwise there'll be no cloud left for which to assemble their mass.
So it's a race against time. If they're there too long, what's the race against time now?
Because they need to assemble their mass from the cloud, and the cloud becomes completely dispersed by the older stars that just got born and then throw the nebula away.
So the longer they're there, the more they can assemble, but the longer they're there, the more that other stars can blow their food away.
That's correct.
Oh, what a mess this universe is. So that's a stellar nursery near us. This is not even in our galaxy. Where is it?
It's in the LMC, the Large Magellanic Cloud, which is a little sort of satellite galaxy of the Milky Way.
Yeah, so once I went out to Coonabarabran, and they said, this is a cloudless night, and it's a really good night, and there's no moon, it's great. And I said, what's that cloud there? And they said, that's the Large Magellanic Cloud. I'd never seen it in my whole life.
There's a small one too. You can get 2 for 1.
Okay, so this is yet another stellar nursery. And here we have So that was just released just yesterday, I think. Now, the way NASA pulled this off, of course, is by having fancy stuff here. And here you can see there's a primary mirror up there, and there's a secondary mirror, and there's the heat shield, and the light comes in from outer space from something from Mars out to the edge of the universe, say 100 million years after the Big Bang they're hoping for. Is that right?
Yep.
Yeah. And then it hits the gold mirror, bounces, hits the secondary mirror, bounces, and goes onto the camera or the cameras, plural. And we're kind of talking here infrared cameras. You're thinking, what's the big deal with infrared? Why do they want to go for infrared? Well, Peter taught me this, so I'm just going to repeat it. He'll tell me what I did wrong. So infrared gives you high redshift, and you measure redshift not with R, but with Z. Yeah, okay.
Got to have a number.
Yeah, okay.
Letter.
And 20 is a high redshift. That means it's really close to the edge of the
Very
universe.
high.
Cold, infrared can pick up cold stuff. Planetary discs around planets as they're forming. And the weird thing is, as Peter's pointed out, infrared goes through dust. Dust is transparent to infrared. There's actually 4 science instruments. Here's one called, what's this called? NIRCam. And yeah, big, I mean, the thing weighs 6.16 tons. So this is a big camera. And over here, we got another one. What's this? This is MIRI, the middle one. And Peter, besides having stuff on hardware on practically every telescope over 8 metres,
Yep.
isn't he humble?
That's me.
If it was me, I'd sort of have it on a shirt. He also has stuff, and I think, did you bring it with you today, the backup model?
Yep, I bought a...
That's it there?
No, Karl, it's actually...
It's several hundred kilograms, is it?
I have it here. So
What?
my instrument flying aboard, the nearest instrument on the Webb, is this. This is an exact replica of what's been flown.
What?
Sorry to disappoint you, Karl. You can put that on a shirt.
That's 2 grams or something. You mean your whole instrument is you got a bit of alfoil and punched a few holes in it?
I thought you said you liked me a minute ago.
Okay, look, I love it. Look, take me through it. What is it? What does it do?
So what this actually does, it blocks out the light of most of those lovely segments we just saw and only allows light through 7 of those segments, selected segments. So in effect, we've just got 4 small mirrors.
Why would you start with 18 gorgeous mirrors and say, I don't want you 11? There's some sort of fancy mathematical reason you picked those 7 things there flying in sort of close formation in perpetual darkness?
That's right. It's like 7 little telescopes flying in close formation. It's a thing that astronomers use called an interferometer, and you've possibly seen these arrays of telescopes marching off into the distance. Basically, we can use the technique of interferometry to get a very, very clear image when the objects are very distant and very, very small.
Peter's also got a little telescope going up privately to find planets around Alpha Centauri. Mm-hmm. Okay, isn't he humble? Okay, so have you got anything coming back yet? Any data?
Well, actually, yes, data has been coming down from the Webb, and this is one of the systems that I've been studying. This is a really hot, bright, ferocious star, Wolf-Rayet star it's called. And we're all clever now, we've all seen the memo. Don't be fooled by the 8 spikes, those are from the telescope mirror. But all of the beautiful nested shells here are all real, they're all on the sky.
Hang on, they're not artifacts?
Those are not artifacts, no.
What on earth gives you nested rings?
So I'm actually not supposed to talk about this because we've got a paper coming out about it soon.
Oh, in Nature, darling.
In Nature, darling.
Oh, yeah, right.
It's a binary star, and the binary goes around once every 8 years, and every 8 years it blows this exquisite bubble of dust, and then another one, and then another one. So what you see here is 150 years of these bubbles all nested inside each other like Russian dolls.
So what, 8, 16, 24, 30, and... Oh,
even older than you, Karl.
Oh my God! I didn't think anything was. Oh my God! So people can have downloaded this photo, which is why Peter's allowed to show it, and you can download stuff at home. And this was you can download this, and there was a citizen scientist who did this thing by herself. And we're looking here at infrared. And by the way, that circle over here in the bottom right, that is that bigger than Earth?
About 3 or 4 times.
Oh my God!
It's the great red spot.
So what else are you looking for besides this sort of stuff?
So my little experiment is all geared to find exoplanets. It's all about planets in the infrared for me. And this is where the Webb and these technologies really come into their own because molecules. The one thing you can really do in the infrared that's very difficult to do in other bands is try to study the chemistry and what actually is present on these planets. So maybe most exciting of all, other than the image you saw of Jupiter, but we're actually getting that kind of data now on exoplanets from Webb. And what you can see here immediately is that this is a spectrum running through the infrared, and those bumps you see are all exactly in the places you would expect there to be if there was the molecule water present in the atmosphere of this planet. This is WASP 39b at 700 light years away. And we're not only finding chemicals like water, we're finding carbon dioxide. And actually, watch this space, because we'll come to carbon dioxide quite a bit later in this lecture.
Can I just ask you, so the planet has an atmosphere, it comes between the star and the telescope, and as it comes between the star and the JWST, some of the light goes through the atmosphere, it's modified by the gases in the atmosphere, and is that how we kind of pick up the gases?
That's right. It's a technique called transit. When the planet transits the face of the star from the perspective of the observatory, you get a little dip in the light, and you can then use that light to do a chemical assay of the planetary atmosphere.
So you're going to try and get not just individual planets, but like a whole solar system?
That's right. So on the screen now, you see, of course, our own solar system, and what we're really hoping for is data of this kind of quality coming from Webb, where we can understand the diversity of all of the solar systems out there in the universe.
And you see up there the third rock from the sun, and if you have a look at it in big, that is the famous blue marble. This apparently is the most copied photograph ever in the history of the human race. It has its own homepage, but then I guess so do influencers as well. But it's deeper than that. And this exists like it is because of why?
Well, what I want to speak to actually is the physics that's being presented to you in this image. What you're seeing here, if you think about it, is the sunlit face of the Earth. All of the energy input into the Earth system is pouring down here in the form of sunlight straight onto the sunlit side of the world. So what that comes from, of course, that comes from the sun. The sun is this ferocious nuclear engine pumping out 10 to the 26 watts, and that's sort of a staggering number of energy in all directions. Earth only intercepts 1/1,000,000th of that sunlight, but that's still 40,000 terawatts of energy witnessed here on the blue marble.
And us humans who think we're the peak of humanity because we've got a forebrain and we came up with poetry, income tax and weapons of mass destruction, all we use is 20 terawatts out of 40,000 that falls on us naturally from the heaven.
So that's the kind of scary number, because all of humanity uses such a tiny fraction. Even if we alter those natural flows through the natural world by a small amount, it's a very, very large amount of energy that we're dealing with in the flow. So astronomers actually have a way of analyzing this in great detail. We can balance energy budgets. We can work out what's going to happen to a planet. And it all is essentially just like balancing your family budget. You've got energy coming in and you've got energy going out. So in our case, the energy coming in is sunlight on that sunlit face. And to prevent the Earth from heating up till it boils or cooling down till it freezes, it's got to be in a steady state. The energy's got to leave at the same rate. And that's leaving by the surface of the Earth in the infrared and radiating out to space. So, in fact, astronomers, when we think about the deeper universe, we're thinking about the same kind of physics playing out in distant solar systems. And we've even worked out a real estate valuation scheme for the universe, and we call it the habitable zone.
That is so Sydney. So over here, that greeny zone, is that what you guys call the Goldilocks zone? Not too hot, not too cold, just right?
That's right. And if you've got around a hot star, like an A star, you better be back away from the fire, otherwise you'll get baked. So your planet has to orbit in a wide orbit.
And then when you go for a cool dim star like that one, you have to cuddle in close. And if you go from the range of hot to cool, as it's got there, you either get further away or you get in closer.
That's right. So here on Earth, we're kind of lucky in a way, because we're sailing in this habitable zone, but we've got test particles, we've got probes, we've got Venus on the one side, on the hot side, and we've got Mars out there on the cool side. So we've got these systems we can use to explore what it would be like to be in those different orbits. So we're going to give you a little morality play with these as our main players. Mars is the too cold side and Venus on the too hot side. And maybe like a lot of people, you might think that the equation looks a bit like this, where it's the parable of Odysseus and the sea monsters.
So you can kind of think of Earth over here, navigating its way between the whirlpool and the big monsters. The big monsters are hot, that's Venus. Mars is the cold one, that fell down the hole. And we sort of in between, and you think, oh, that fits in with the distance. It's more complicated. Everything in physics is more complicated than that, isn't it?
That's right. So we're going to tell you about how it's not quite as simple as that. That is a big factor. But in order to really set up the physics of a planet's temperature, you need to think quite a bit harder than just that simple paradigm.
So the first thing you go for is obviously the distance from the star and how bright it is. And then you've got 3 factors. First one, you pretend that your planet is just a dumb ball of iron that absorbs everything. Then you add a second factor, which is how reflective it is. And then you add a third factor, which is the atmosphere. And then when you run through it, you'll find, looking at if the planet was just a ball of iron, that is making perfect sense, because Venus would be the hottest, and then you go down to Mars being the coldest. Out of the 3, that fits in with the distance. But then you add in the reflectivity. Now, there's something weird going on about Venus, which I never appreciated until you told me, Peter.
Yeah, so if you add the albedo, if you want to use my fancy astronomer term for it.
Fancy astronomy to albedo.
I can use them. You can now see that Venus is at minus 41, and Venus is actually colder than the Earth, because almost all of the energy that lands on Venus gets reflected back out into space. It's like a shiny disco ball. So, very hard to heat it up.
So let me get this straight. So now that we've gone the black ball and we've added reflectivity in the equation, Venus, even though it's the closest, is the coldest?
That's right. You can see here Earth, for its reflectivity and its orbit, should be about minus 24. So we get minus 18, sorry. So we're getting a bit chilly here on Earth. We better do something, Karl.
And then we go to the next stage where we chuck in the atmosphere. And when you chuck in an atmosphere, you see that Venus goes off the charts. That's what lots of carbon dioxide does for you. Forget 1.5 degrees. That's like 500 degrees, and you work your way through into Earth and Mars. So that's just a massive nub. There is some atmosphere on Mars, but it's about 1/160th. It's not up to the job of keeping the planet warm enough, is it?
No, Mars has got a very thin atmosphere, so these numbers don't change much, you'll see. But you can see Earth, without the greenhouse effect, would be down there at minus 18. So we need that greenhouse to bring us up to a comfortable plus 15 on average. So let's continue with our morality play when we've got a scorching hot, hellish Venus, and we've got a frozen desert on Mars, and it's quite nice and balmy here on Earth. So how did things get this way, and what happened to Mars and Venus along the journey? So let's just start with Venus.
Yeah, so what went wrong with Venus? It is close to the sun, but was it different in the past?
Yeah, so there's very new research, in fact, done in the last few years, that the consensus is moving towards the fact that Venus may have had a habitable climate, may have been a temperate world for up to 2 billion years, half its history. How could it pull off a trick like that? Because it actually is quite close to the sun. Venus, it turns out, has a very slow rotation, and the models that we have now say that as that slow rotation goes around to the day side, an ocean would boil up and give you a massive shield of clouds facing the sun. But then because of this long, slow night, the clouds all dissipate and it gets quite clear. So the planet is able to vent the heat to space on the night side and build a shield on the day side. So Venus was able to pull off this incredible balancing act, we believe, for half its history. But unfortunately for Venus, the music stopped one day. It is quite close to the sun. Maybe a big volcano went off or something and spiked the carbon dioxide in the atmosphere. But this was a bad day on Venus because it passed the tipping point and the oceans boiled. And when your oceans boil, you're really in trouble. You ended up with a runaway greenhouse effect on Venus.
Okay, so catastrophic, irreversible. Okay, so Venus had a bad day. So what's the story with Mars then? How did Mars go here?
On early Mars, we know for sure that there's actual physical evidence that we did have lakes, we had oceans, we see rivers. In fact, another fun fact, Mars has a very asymmetric shape, and if it's got lowlands all to the north, if it ever had an ocean, it would have looked perhaps rather like this. So Mars definitely had a temperate climate early in its history, but unfortunately for Mars, it also ran off the rails. It's a little bit too small. You need gravity to hold onto that dense atmosphere. It doesn't recycle its volatiles through geological processes we'll come to later. And because it doesn't have a dynamo in the core, it doesn't have a magnetic field, the solar wind comes in because there's no magnetic shielding, and it strips the atmosphere away over time. It erodes it.
So on Earth we've got a magnetic field, and if that's the sun there, when a big solar storm comes, it wraps around. You only get auroras at the north and south poles, not at the equator, unless it's really enormous. So is that the magnetic field that we've got, and that Venus is
if we didn't have it, our atmosphere would have been eroded too.
Right, okay, gotcha, yep. So, poor old Mars.
So, the same story, Karl.
Yeah. So what we're looking at is out of the 3 planets we're talking about, 2 of them went to lunch, leaving Earth in a very nice place. So how do all these factors play out with regard to Earth managing to survive? We survived. We're here. We're alive.
So you remember a couple of slides ago, we saw that Earth should be actually quite chilly, and it bumped it up. The greenhouse effect bumps us up to this average temperature of 15 degrees. And we're going to go on a bit of a deep dive into the physics of the greenhouse effect now. So the way it works is that the sunlight comes in here in the visible, some of it in the infrared, the near infrared, and this is the energy input into the system. But when it comes to cooling the Earth back down again, so that everything stays in balance, the radiation going back up into space happens at room temperature. It's heat radiation. It's the thermal infrared. It's where the Webb works. So what we need is, and you can see on this chart straight away, about 70% of the sunlight rains down and it just comes straight down to the Earth to warm it up. But when it's trying to go back up, it's a much harder job because those molecules in the atmosphere act as a blanket, and only about 30% of it can easily progress back up to the atmosphere. So, Karl, I kind of think it's time that we did an experiment, a lab experiment on climate change.
The fossil fuel companies have been doing it for the last century. Why can't we do it?
Exactly.
Okay, so where do we start with our experiment? We've got ourselves an infrared camera there.
That's right. That's the noise people in the near audience can hear.
Okay, so we switch through to the infrared camera here. Oh my God, that's
right,
you.
Karl. Come over here.
Hang on.
So you're the. All right.
Right. Okay. Yep. Okay.
All right.
So I'll stare down the barrel.
So this camera is working at about 4 microns in the infrared, and you can see Karl's wearing what look like very dark sunglasses, but in fact the audience here can see they're in fact just normal spectacles. So this is telling you something straight away. The light from the sun would reach Karl. So Karl, you're our little stand-in for planet Earth.
In the trade, we call this, I have been demoted to the warm prop.
You are the warm prop for this demo. So Karl's glasses are showing you that the light can get to his face in the visible, but the light can't escape. He's got a blanket on his face, and we'll give him a rather better one. So this is just a sheet of normal glass. Have a play with that and see what that does to your thermal. So you can see he's now very much behind a thick thermal blanket. So this is called the greenhouse effect for a reason. It's because you use glass in greenhouses to perform this piece of magic for you. If you live in the northern hemisphere, way up in the, perhaps you're in England somewhere, hard to grow veggies, you can keep your greenhouse nice and warm with this one-way magical trick. And glass has a superpower. It lets the sunlight in, but it doesn't let the heat back out again. So this establishes part of the physics of the greenhouse effect. But Karl, I want you to put your body even more on the line here. It's all for science.
I'm the warm prop. That's why I get the big bucks.
We need to show you that carbon dioxide is in fact also a greenhouse gas. And carbon dioxide will act in the same way as that sheet of glass. So just pretend your body's on fire.
Okay, you got the pin out. Okay, my body is on fire. Okay, right. Okay,
ready?
Blow it. Yep. You can't see anything here with your visible light. But the infrared sees it. Let me just tip out some of the ice particles. Okay, do that again, Peter. I'll do it from sort of this angle here. Okay, so do it across my body gently. Yep. Wow.
So
That's carbon dioxide. Is that right? It's blocking the infrared?
carbon dioxide's forming a molecular blanket. The 4-micron light that this camera is sensitive to, the thermal light, the light the Earth needs to radiate back to space, is now blocked. It's opaque. You've put a blanket over you. And in fact, we've got some dry ice in this cup here.
Which, by the way, the entomologists use as their way of attracting insects. They go out with a cup of dry ice. Okay, so what I do is
you're the warm body. You're the dummy as well. You need to pour the carbon
oh my
dioxide.
God, am I pouring carbon dioxide out?
You're pouring carbon
Okay,
dioxide.
shake it up again. Oh my God.
This is simple. So
Okay, right. You do it too. Go on. You deserve some stage time.
I mean, you can also see a little bit of condensation here, but in front of my warm face, you can see
Oh my
the
God,
action.
that's much better there, isn't it? Face, you say? Come to the light.
So I don't know if you can see that, but Karl is breathing out carbon dioxide. There's no condensation. If you do that again to the camera, Karl. We did know Karl was full of hot air, but he's also full of carbon dioxide.
And you are backing up what Andrew Bolt has said 7 times about me.
But we also should point out why Karl is breathing out carbon dioxide is because he's eating carbohydrates. Karl is an engine that turns carbohydrates into carbon dioxide. A power station is an engine that turns hydrocarbons into carbon dioxide. Living organisms breathe out carbon dioxide. In fact, Karl used to be a doctor, and they would use a machine that's tuned to this exact wavelength to witness whether the patient's still alive. If your exhaled breath has no carbon dioxide in it, this is a bad indication for the doctor. Your fingers are too cold, Karl.
Yeah, so what happens is you've got these people called anaesthetists. Now, as you know from the movies, they're all cons because all you have to do is throw out a grenade and everybody just falls asleep instantly in all the movies, from the anaesthetic. Why do they go to a university to study for 10 years? We don't know. So what they really do is they sit there doing the crossword and they're listening to the machine that goes beep. And why it goes beep is that their air is coming out as they breathe. And there's a laser beam. It's an infrared laser.
It's a detector that's sensitive to this radiation.
And every time carbon dioxide comes out of their lungs, so 20% oxygen comes in, and what goes out is 16% oxygen and 4% carbon dioxide. And every time that carbon dioxide that you breathe in goes out, that's 15 times a minute, it blocks the infrared. The machine goes beep, and then they try to say, a number of men. And by the way, the answer for that clue is that you don't pronounce it number of men, but number, something that makes men numb. Of course, the answer is ether, an anaesthetic. See how it wraps around? Yeah, okay.
Sorry, Karl.
Too hard. Okay, I'll push that one too far. Okay, we're out of the experiment. Where are we now, Peter? Let's get our little clicky things going.
Yeah, we better get back on track.
Yeah, okay. Oh, and by the way, the amount of heat that the carbon dioxide captures as compared to 1850 is 600,000 Hiroshima bombs per day. We were talking about that massive change in air flow. And we're heading into the concept that there's a thermostat for the atmosphere. Who knew? What? Hang on, let's just go. I didn't get the memo saying there was a thermostat.
Yeah, so it's a good question. How did the Earth avoid the fate of Mars and Venus? How did we stay on that line? Why didn't Earth fall off the wagon the way they did? And it turns out we have a thermostat. And this is a thing called the carbonate-silicate cycle. And it works a bit like this. So imagine volcanoes. They're always spewing carbon dioxide up into the atmosphere. That's dissolved by rain, and it falls down as a weak acid called carbonic acid. When that hits the rocks, it starts dissolving the rocks. That's where limestone caves come from, for example. And then it all gets washed to the bottom of oceans, ends up in sediment, and it gets down into a geological record, only to end up getting vented up by a volcano again.
So that's the geological cycle of the carbon atoms going round and round. Where's this thermostat thingy?
Yeah, so the thermostat works like this. It's actually quite simple. If you just imagine for a minute that the climate gets a bit colder, then there's more land area under ice and snow, less rain falls onto the rocks. There's less weathering, there's less carbon dioxide deposited in those sediments. Carbon dioxide still coming out the volcanoes, got to go somewhere. It goes in the atmosphere, it stays there. Carbon dioxide in the atmosphere, boom, global warming. It's a negative feedback cycle.
So it's a negative feedback cycle. So if you chuck in some coolth, it warms up. What if you chuck in some warmth?
So the opposite happens. You end up with a warmer world, more rain, more weathering, and more carbon dioxide scrubbed out of the atmosphere. In fact, there's a belief among geologists that the rise of the Himalayas and the extra weathering on the Himalayas precipitated the present cold snap the Earth has been experiencing. That's why we have our climate we do today. So warmth, by the same cycle, leads to cooling, more rain, more weathering.
And that was 40 million years ago when India rammed at roughly the speed your fingernails grow at, 5 to 10 centimetres a year, into Asia and gradually pushed up the Himalayas, massive weathering. And the bar-tailed godwit, I think, was flying across that area, and it kept on flying. And now they're stuck with having to fly over the Himalayas. They're the only bird that can fly over the Himalayas because the Himalayas just kept on rising on them. Okay, so this is fantastic news. We have ourselves, look, there it is, it says so. We have a thermostat that keeps the temperature nice and wonderful. What's wrong with that?
Well, there's bad news, Karl, and that is that thermostat takes about 500,000 to 1 million years to kick in. And the other piece of bad news about the thermostat is that the typical set point, the typical temperature of Earth is way too hot for civilization. Earth is normally much hotter than it is. We normally don't have polar ice caps.
So the moral of this play is we've had climate change on Mars and Venus. In each case, it has been catastrophic, and in each case, it's been irreversible. We, however, are lucky, and we have some sort of process, a biological process, and we're big enough and we're in the right place, blah, blah, lucky us that we've stopped it from going off the rails. But then these won't necessarily help human civilization if we try to go into things too far. So we're heading towards the end of our morality play here, and we're looking at Earth. Now, this is a weird concept.
Yeah, there's a final point to make, and that is that there's also biological processes maintaining this. Earth has a very rich, very deep carpet of a biosphere. There's lots of organisms. They all contribute to the chemical environment of the atmosphere, and that in turn changes the atmosphere and changes this energy balance. So Earth is alive. It's a geoengineered planet. So there are lots and lots of these systems all working in parallel to maintain the climate the way it is.
And so Earth's been kept where it is by the geological and the biology. The atmosphere is due to geology and biology, and we are biology, and we've been changing stuff. We have been changing carbon dioxide levels faster than at any time in history. And here's an example. Look at this picture here. This is from NASA. And they said, hey, we had a big PR thing happening with a blue planet. Let's have a photograph of the nighttime sky. And the obvious thing is over Europe, etc. There's all these lights going on. But then when you dive in a bit closer, you see something different. Take us there, Peter.
That's right. This is a thing called the black marble. It was to follow on their blue marble hit. And it's actually a photon montage. But people started studying the data that NASA were taking really closely, and you can see strung like jewels on the interstates of the North American highways, all these cities. But there's a big city there. That's about the size of Washington or New York, if you look at it. And it's in the middle of North Dakota. And people were saying, scratching their heads, going, hang on, there is no big city in the middle of North Dakota. What you're actually seeing there is the Bakken Shale Oil Formation, and the light is all coming from gas flaring. So this is a thing that the miners use to vent off unwanted methane. And believe me, burning it is rather a lot better than actually just allowing it to vent without burning it. But you still end up with lots of waste carbon dioxide into the atmosphere.
And here's the weird thing. They're burning up enough methane to run Australia 24 hours a day. How can they afford to do this? Let me introduce you to two words. One is called investment. If I give you $100, I expect back $105 after a year or so, I'll get a return. The other is a subsidy. Here, I'm giving you $100, walk away with it. The fossil fuel companies have had subsidies, and we've measured it since about 2013 and 6 years earlier. These figures come from the International Monetary Fund, and it turns out that the fossil fuel companies get 8% as a subsidy, not an investment. You've heard of the diesel subsidy? That's a microscopic part of it, of all the money generated on the planet Earth. What will happen over the next 5 years depends on how you vote. The latest thing coming out of Yale says that the latest figure we've got is $5.9 trillion. And you think, that's a number. Where does it fit into the scale of things? Yeah, it works out as roughly 8% of all the countries on Earth, all 200 working together. The total amount of income they make is $85 trillion, and that sum is roughly 4 times the world military budget. That's given for free as a present, on top of the money they earn, as a present, as a subsidy to the fossil fuel companies. It's 5 times what Australia earns and 85 times what we spend on things like the Just Wonderful Space Telescope and everything else. And these fossil fuel subsidies, they're in direct and indirect forms. They don't have to pay for the 20% of the population they kill by air pollution early every year. And it turns out that half of that money, 4%, is all we need to stop and reverse global warming, climate change. If we take away their fossil fuel subsidies, we can then spend 4% on fixing up climate change and the other 4% on, I don't know, foolish stuff like health, education and welfare. You want to know more? Here's your homework. Get this document here from drawdown.org. Drawdown.org. It'll take you as long to read it as a grand final. And the Australian version is this one, Zero Carbon Australia, and they deal with a local point of view. And you'll notice down the bottom they say the Million Jobs Plan, and you think, oh, that's good, because really the mining companies and the fossil fuel companies employ huge numbers of people. They employ less than McDonald's. They employ fewer people than McDonald's, and the jobs are not FIFO for local work. For local renewable stuff, it's local. For fossil fuel companies, they're away 4 nights, they're home 4 nights a month, and the family falls to pieces. You don't want no FIFO. So we can go zero carbon for electricity, which is roughly 15% of our emissions in 10 years or so. Steel and concrete, another 15%, same sort of time period. Transport, same sort of time period. Agriculture, mixed. And the only thing stopping us is the political will and 4% of the world's GDP. Now, you might have come across, a little show of hands, I only learnt this phrase 2 weeks ago, so I'm acting really cool. Who knows what TLDR stands for? Okay, yeah. Okay, it means too long, didn't read. So instead I've given you a THM, which is the take-home message, which is very straightforward. We do not have to adjust. We do not have to put up with 50,000 people in Sydney being evacuated every year when the floods happen. We can reverse it. We do not have to adjust. We don't have to adjust. We can reverse it. We don't have to keep on giving money to them. Instead, we use it on something worthwhile and with today's technologies and their money. Now, one thing that my parents taught me was that the best camera that you can have is the one that you have with you. Nah, this is the best one. So thank you very much, and we'll now move on into thanks and so forth. Thank you.
Thank you. Yeah, special thanks to Connery and Lucy, who are here today.
Give a wave,
and
give a bigger wave. That's
I'm
it.
gonna-
Aren't they lovely?
A warning to the audience, if you're going to ask a question, you're going to have to ask your question in the infrared to Connery.
So thank you for coming. Remember the Slido thing, SLIDO, nothing to do with hamburgers, Sydney Ideas, capital S, capital ID. And so while you're thinking up your questions, either biological here in the theatre. Now, I think we see a microphone, is that right? Well, look up the back of the room, there's microphone 1 and 2. So do people wave and then you come to them? Is that what happens?
Connery.
And then also, Fenella was going to give us some questions.
Indeed. So if you have a question for another round of applause by the way, Peter.
Thank you.
Okay,
They're looking at themselves, Karl.
as Peter was saying, we can all afterwards come and have a look at ourselves in the infrared. If you do have a question and you are in the room, put your hand up and one of our amazing friends on either side will come and bring the microphone to you. Don't be shy. If you are at home, you can use slido.com and the code is Sydney Ideas. If you're feeling shy in the room, you can also go to slido.com and pop your questions in there too. Use the code Sydney Ideas. While the questions are coming to you, I'm just going to, a couple of people have sent in questions beforehand, Karl and Peter, if I don't mind throwing a couple of them at you. So a couple of people at registration. So Peter, the first one's for you, was thank you for your time. Regarding the placement of the Just Wonderful Space Telescope, could you please outline why the benefits of its location so far out of reach, at least with existing technology and expertise, outweighs the ability to access it when, if not if, it will require repairs or upgrades? And what's the decision-making process that was in regards to its placement?
Yeah. We can't get out there, can we?
Can you do it?
Yeah, so the question's a good one. It's out at L2, which is the second Lagrange stability point, and it's way out there because it's out in the deepest, darkest, coldest, most infrared quiet spot we could find. So it can hear those whispers coming from the distant cosmos. And it's way beyond any possible servicing mission. In actual fact, most missions are beyond servicing. They're not built to be serviced. Hubble was the first one that ever even conceived of flying an astronaut and tinkering with stuff and going back. And I think it may be the only one that's ever done that. So Cassini, all of the space probes that are equivalently large and ambitious, they also rely on 100% duty cycle for their equipment. A single failure might cripple the whole mission. So this is not such an unusual paradigm to be working in. But essentially, the trades are very difficult to manage. If you ever wanted to potentially service a mission out there, you wouldn't be able to really get astronauts there and back for an affordable amount, and you might end up that the cost to send an astronaut there and back would be more than the cost to just build another mission in the first place.
So with your little disc, your 50-kilogram disc, was it made of some sort of unobtainium that would outlast the pyramids in the universe?
Funny you should ask, Karl. So the one in my wallet is made out of just shim aluminium, and I just sent this to NASA saying, here, you can just put this in because it's already just the right size and everything. I'm like, oh, no. They had to make it. No, so they had to make it out of, in fact, a depleted metal. You've probably heard the term depleted uranium, which is a slightly scary thing that's used in military rounds. A depleted metal is a metal with a very low radioactivity, a very high purity metal. You ask, why would they care about a piece of shim being a depleted metal? It's because this piece of metal is near a sensor, and the sensor is a very sensitive sensor, and if it's spitting out little radioactive particles, all of the surrounding camera that's near the detector is going to be radiated by the material you flew up there to make the spacecraft with. So they make it out of special high-purity materials for that reason.
Right, and in fact, we all carry in us radioactive decay from, firstly, cosmic rays coming into us, but also from the atom bombs going off. And apparently, the iron on some Roman ships 2,000 years ago is highly sought after because that's free of the radioactive decay from atom bombs. Depleted metals.
We should move to another question.
Lots of questions coming through on Slido. We're going to the question up here just at the back there. Thank you.
Thank you for today. I just wanted to, if you can comment on the ozone thinning and holes that we hear about in terms of what you mentioned today.
Oh, well, I could grab that one. That's a wonderful, feel-good story that has a great ending. So when the ozone hole was first discovered, it was discovered, in fact, by Antarctic scientists, and immediately swung into action a system of protocols and a treaty. And within about, I think this was the Montreal Treaty of about 1976. I'm trying to dredge that. 80 something.
Yeah.
So it was a Montreal Treaty that banned so this is from CFCs, from the refrigerants. And it was a fairly small economic sector that was impacted, but it was kind of impacted because the CFCs that existed were replaced by things that weren't as good. So it was, they had to take a hit in order to remove that product from the marketplace. But it's a beautiful feel-good story because it worked. Basically, the ozone hole has largely recovered now. We see all these feel-good reports about this. In fact, the parable of the ozone layer and how we did organize as a race to fix the ozone hole is often translated to why the heck can't we fix the carbon dioxide problem and the climate change problem,
I know.
which is much more existential threat to everyone's existence. I mean, you can wear sunscreen, but you need air to breathe and water to drink.
From 1973, when the insurance company said that global warming was real, till 1990, the best research in the whole world was done by the fossil fuel companies. Then they chucked a Yui and started spending $1 billion a year on telling porky pies. Read my book, Dr. Karl's little book of climate change science. $10 is a bargain.
Okay, we've got a couple more questions in the room. I'm just going to go to one from Slido. There's actually a couple here, Karl and Peter, that kind of, I think maybe similar.
I'm just moving back into the camera view, Peter.
Yeah,
That's us,
so
yep.
question from Andrew. Could there have been life on Venus when it was more habitable? And just to continue on, can the James Webb help us find life on another planet? Another question, how can JWST detect life in other solar systems? So a couple of questions
For me?
such as that, I think, for Peter or Karl. Yeah, go for it.
The first one was?
Could there have been life on Venus
Absolutely,
when it was more
life
habitable?
on Venus. People are very excited about this. In fact, could there still be life on Venus? This is an open question. People are thinking, I mean, if you go about
80 kilometres?
I think it's about 80 kilometres in the atmosphere. There's an area where the temperature is about room temperature and the pressure is about the same as the pressure in this room. There's a 1 atmosphere room temperature layer in the atmosphere. And Venus also has these unusual, it's very shiny, it's very white, but it's also got these kind of vague stripes. And no one quite knows what those stripes are. And the people who are very excited about this think they could potentially be algal blooms or something in the atmosphere of Venus. So people are interested in dropping some kind of craft into the upper atmosphere of Venus to see whether the life which may have been there at the early stage could have migrated up into the atmosphere as climate change forced all of the other ecosystems out of business.
Can Webb find life?
Can Webb find life? That will be a stretch goal. It will be very difficult. There are chemical traces. We talked about the infrared. The infrared's really, really... Sorry, I need to be in the infrared when I'm talking about the infrared. So the thing you want to look for, believe it or not, and we just had a question about ozone, is ozone. Ozone tells you you don't care particularly about ozone, but you care about oxygen. So Earth is just a weird planet. If you look everywhere else in the universe, there's no oxygen. Oxygen rusts. That's what your car is doing all the time. Oxygen wants to react with something. So oxygen is a very reactive molecule. The fact that we have oxygen in our atmosphere places Earth out on this weird spectrum. And the finding of, it's called non-equilibrium chemistry. You shouldn't find it. It's like finding free food or free money just lying around. Free oxygen shouldn't exist chemically. And because it's so unusual to form abundant free oxygen chemically, the finding of free oxygen chemically drives the idea that it was put there by life, which is the way it happens here.
But oxygen is just outside the JWST infrared band detectability? Or can it just pick up a bit of oxygen?
No, I think there are ozone lines within
And the
Webb's
third
reach.
question?
How can JWST detect life in other solar systems?
Yeah.
Yep.
Yeah, look for the oxygen, I think,
Yep.
would be
Look for
the
the
answer.
oxygen. Okay, so thank you, Tim, for your question. Let's go to some more in the room. I know one of our microphones.
Biological.
Whoever has the microphone, go for it. Thank you.
I think you half stole my question, but it was actually on those other gases because looking for life, water is amazing to be able to see, but it's the other one. So apart from ozone that you mentioned, are there other gases that indicate life that we reckon WST can pick up?
There is a thing, if you look, so they actually, what scientists do is they use telescopes in space that were normally designed to go look at Mars or Venus or something, and every now and then they turn them back and look at Earth, and they get data from what Earth looks like. And this is a beautiful data set for scientists to have, because you've got an example then of what life looks like from the outside. And vegetation, it has a thing, it's called the red edge. So if you look at the spectrum, there's this characteristic rise in the red and it's due to chlorophyll and due to all of the abundance of life. You don't find it where there's not life. So these are called biosignatures or biotraces, and there are other gas. Methane is another gas that you can look for, but methane often exists independently of life. But the red edge and the presence of oxygen betrayed by ozone are often, and then you can find oxygen sometimes with non-biological processes, so then you start to look for balances. You want a bit of this one and a bit of that one in the right the right ratio. So it becomes more a difficult game if you really want to cross every T and dot every I.
Okay, question for the audience. Who reckons that within 15 years, JWST will categorically say that there's life somewhere? I reckon there is, but I'm probably brain damaged because I've read too much science fiction. Am I the only one to... I'm saying, 3-5% maybe, Peter? Yeah, I mean, in the audience, that's what we're getting. Yeah, okay. Just a nice survey. Okay, next.
Yeah, I think we've got a question from a person just here. Thank
hello.
you. Hello.
Thank you for coming in tonight. Thank you. Talk loudly, please.
So, what is Australia's contribution to the James Webb Telescope?
Well,
It's about this big.
let me just...
Look, we will let you touch it. Is that okay?
Well,
and
this-
there's all the research.
you've
we
already
do.
seen my mask.
Yeah.
Australia is not an official partner in this mission. Lots and lots of Australian scientists are applying for time. Lots of Australian scientists are in... The way astronomy, like a lot of science, is done these days, is in very large international teams. And Australian scientists have a very, very strong... We have a very, very strong astronomical community in Australia. We sort of used to have the Southern Hemisphere all to ourselves. We were one of the powerhouse countries in the Southern Hemisphere doing astronomy. And in fact, it's not a very democratic sky. The southern sky is much more interesting to an astronomer than the northern sky. We've got the galactic center down here, sorry, north. We've got the large Magellanic Cloud and the small Magellanic Cloud. We've actually got lots of things of which there's only one of them. And you can only study that thing from the south. So Australia has a very, very strong astronomical history, and that's printed through into participation in projects like Webb and all of the big mega missions that are being launched by NASA and ESA. So even where we're not actual buy-in partners the way NASA and the Canadian Space Agency and the European Space Agency are. So the MIRI camera that we talked about, and the camera here, this infrared camera, is a little brother of a little brother of a little brother of the ones on Webb. It's the same wavelength. That camera was built in France. So there are countries that have bought in, and my little disc that's flying on a Canadian instrument called NIRIS. So there are international partners, but Australia's not an official one.
For sure. Thank you. There's a question, microphone just here. Thank you very much.
Thank you. Thank you for your presentation.
Thank you.
A few weeks ago, I heard on the radio and on the television about the voice of the universe. And they said it was B flat, 57 octaves below middle C. So can you explain how they detected it and how you can have a voice of the universe through space?
By the way, if anybody has to go, babysitting, dinner appointment, now's a good time to go, and we won't pick on you. But if you want to stay, we love you. The process is called sonification. It turns out that because of evolution and our brains, over a period of time, turning sounds into sense, our ears internally are hooked up to massive intelligent processing units. And so we started using sonification way, way back in Grecian times when we listened for the sound of a little probe hitting a stone in the bladder. More recently, we used it in the Second World War, where in radar and sonar, instead of just looking at a screen, you'd hear a beep, beep, beep. And now, over the last 10 years, we've moved into getting data sets like the age and sports activities of primary school kids in a certain area. And if you map that onto sound, you can then listen to it and pick up different trends. In this particular case, what we had was a black hole. The black hole had around it a big cloud of gas and dust. And the black hole, as stuff was falling into the big cloud of gas and dust, it would hit the cloud of gas and dust, and then sometimes it would bounce off and come out, and there were shock waves coming out, which then changed the makeup, the distribution of this big spherical cloud of gas and dust. What was done for sonification was they started off at the center point, and they got a probe, and they then assigned different parts of the spectrum to different instruments. So if it was X-rays, it might have been the French horn. If it was gamma rays, infrared, etc., etc. And then they had brightness, how much there was, a lot or a little, and that was loud or soft. And they did a whole complicated algorithm to assign different bits of information to different parts of the sonic spectrum. And then they swept it around slowly and then you could hear this bit, and you think, oh, I'm hearing what I heard here, I heard over there. So that was the sound you're referring to. It was a little bit exaggerated.
Fantastic. We are going to get a question from this young man here. Thank
Hello.
you very much. Hello.
Do different atmospheric levels have different reactions to greenhouse gases? And if they do, how do they affect Earth and outer space?
Different greenhouse gases have different
Atoms in them?
Yeah, so different gases do behave very differently in the sense of a greenhouse. So you saw what greenhouse is. I can do the demo again. A greenhouse is when you can have light energy coming in at one wavelength, but it can't get out again when it needs to get out at a different wavelength. So my face is taking visible light, it's warming up in the visible light, the sunlight say, but then it needs to re-radiate that and lose that in the infrared. So carbon dioxide is one greenhouse gas, but a much more potent greenhouse gas is methane. So methane is very, very absorptive. It makes a very thick blanket. In fact, for one molecule of methane is about equivalent to 80 molecules of carbon dioxide. So very, very much depends on... So that's why I said when we're flaring that methane coming out of the natural wells in the Buck and Shale ore formation, it's way better to burn it and turn it into carbon dioxide than it is to let the methane out. That's 80 times worse, just letting the methane out. So the chemical species of the gas matters a lot. And in fact, one of the worst greenhouse gases of all, it's not actually considered a greenhouse gas, but water vapor. Water vapor is very, very strongly absorbing all the way through the infrared. So if you have lots and lots of water vapor in the atmosphere, that will also cause a blanket. I mean, you've seen this at night. If you're out at night and you have a nice clear sky, everything gets cold. Your car is cold on top. It's all frosty. If it's a cloudy night, it's balmy and warm. So this is this blanketing effect in action, and planets need to balance these blanketing effects so that they can keep their temperatures stable.
Fantastic. I think we've got time for a couple more questions. So before we go to that one, a really quick question, if possible, from Slido. Again, thank you for your questions, everyone. Here it is. I've just gone and lost it. Can we use James Webb to monitor biodiversity on Earth?
No.
Great. Quick.
Because
I was like,
I will elaborate.
Okay.
Because they would shoot you. So they will not turn... So you saw that beautiful big tennis court-sized sail that absorbs, that takes the pounding from the sun, kilowatts and kilowatts, and it's only a laser pointer going up. It's an exquisite engineering thing. If you turn the telescope upside down, it's getting baked by the full blast of the sun. Everything would bend, everything would warp, and they would frog march you out of the control room and throw you into the sea.
All right, you'd never be able to do an experiment
so
ever
the telescope
again.
cannot look, not only can't look at the Earth, it can't look anywhere into the inner solar system. And in fact, you have to be very careful what you can observe on a given night, because the telescope has to very carefully maneuver itself so that sail is always blocking the sun. So it's got quite a limited range of things it can look at on any given night, because it can't just turn around and point anywhere.
But over 6 months or a year...
Over 6 months, it gets a view of the sky, so you just have to be careful with the scheduling.
Okay, thank you very much to Anonymous for your question. I hope that answers it for you. And we've got a question up here. We'll do 2 more questions. Is that okay, gentlemen? Yep. Thank you.
Yes, so I worked with synthetic aperture radars for a bit, so interferometry sounds really familiar. So I was wondering, in your context, what you're trying to achieve by doing this, like you're trying to increase the resolution, or looking for things you otherwise wouldn't see, or, like...
What are you trying to achieve with your
This is with the little mask.
kilogram disc?
Microgram.
Okay.
Yeah. So the activity interferometer is that you break the mirror into a number of small beams. And a sort of a common sense analogy is that 2 eyes are in fact better than twice 1 eye. You get binocular vision. You get new things by hooking up 2 eyes in concert than you do for 1 eye. It's a little more complicated than that when you go into the physics of it. But in essence, even though Webb is out there in this exquisite dark cold and there's no atmosphere to contend with, it's got a very, very clear view of the heavens, it still turns out that by performing interferometry with separate pieces of the mirror, you've actually got a simpler question you've asked. You have simplified the information coming to the detector. And when it's been simplified in that interferometric way, you can actually get better measurement precision on that data. It's like you have less data to start with, but the data you have recovered, you've recovered at a higher fidelity. So you can actually exploit that to look for very, very faint things next to very, very bright things. And a planet is very, very faint. This is something people maybe in the public don't quite realize, the daunting challenge of looking at a planet. We talk about, let's just go look at planets. Why don't you just turn the telescope there? It's not nearly so simple. A star outshines a planet by the same ratio as the brightest modern lighthouse lamp staring straight at you compared to a very, very sick glowworm. And that very sick glowworm is crawling about 1 millimeter away from the searchlight. So we have what's called in astronomy a contrast ratio problem, a contrast problem. We're staring into the brightest possible light, that's the host star. If you want to find a planet, it's in orbit around a star. And from the distances we need to observe, it's not like we can look and there's Mars and there's Venus. The star you're looking at's there, and the planet you're looking at is right next to it. So it's a daunting problem, and that's why we need this interferometric technique.
It has been extraordinarily wonderful to hear from Dr. Karl Kruszelnicki and Professor Peter Tuthill. Thank you all for your amazing contributions and your questions. Give them a round of applause. Thank you.